Hello and welcome back. Today's lesson is about proportions and direct variation. You've already seen proportions before, and we actually know how to solve them. I just never really told you that you were doing it. So today we're not going to learn a whole lot that's new, except the part about direct variation and how to recognize it and how to work with problems that involve it. So hopefully you have your guided notes ready. I've got my coffee ready, so let's begin. And I'll scroll up a little bit so we have some space here. And we'll start off with a definition. What is a proportion? And a proportion is just a statement with math, of course. And the statement says that two fractions are equal. So for example, over here on the right, we've got a little bit of space. We could say that one fraction a over b is equal to a different fraction c divided by d. And of course, you've seen things like this before. We worked with proportions when you were creating equivalent fractions, when you were finding common denominators. So, and we've even solved equations involving two fractions where one of the pieces was missing. Most recently, we've looked at Charles's laws. So, just because it's fresh in our mind, let's see if we can't write those down. One of them is V1 compared to T1 is exactly the same as V2 compared to T2. So if the volume of a gas increases, it's because that temperature has increased, and the ratio of the volume to the temperature stays the same. Do you remember how the other one goes? It involves pressure and temperature. So P1 compared to T1 is the same as P2 compared to T2. If we're going to solve a proportion, we solve a proportion the same way we solve any other equation. Our job is to find a value for the variable that makes the equation true. All right, so let's get started and we'll try a few examples. The first example we're going to do is not going to have any context in it, although maybe you recognize the units pounds in the numerator and square inches in the denominator. This could be something that involves pressure. At any rate, it doesn't matter. What we're going to do to begin with is to solve this equation in a very careful way and keep the units involved in our calculations all the way through. So here we have one fraction equal to another, and you know that in order to isolate this x is being divided by 6 square inches, so we would multiply both sides of the equation by 6 square inches. Since we have fractions involved, that multiplication, of course, happens up in the numerator. So we have 6 square inches multiplied by that 1,130 pounds, all divided by 5 square inches. And that will be the same as, right, x in the numerator. Again, we'll multiply by 6 square inches on both sides. There. So we've got our original fraction on both sides with an extra 6 square inches in the numerator of each one. And the reason why I wanted to keep the units involved this time was so that we could watch all of the interesting things that cancel. You already know that common factors cancel. So for example, here the 6 compares with the 6. And maybe you remember from some times ago that we did this, that common units also cancel. So square inches here cancel with square inches there. Over here on the left-hand side, square inches cancel with square inches. I'm not particularly worried about the 5 as a common factor up here. That'll all come out when we start calculating. But what I want you to see is this. On the right-hand side, Of course, x is alone. That's our whole goal, and that's why we did what we did. But on the left-hand side, we have a 6. We have 1,130 pounds. Right, pounds are still there. They didn't get canceled out. Divided by 5. So when we get done, the answer is going to have units of pounds already attached to it. We don't actually have to remember that x is supposed to talk about pounds. We can tell it because that's what the math says. All right, let's get ourselves an answer here. 6 multiplied by 1,130 and then divided by 5. And the answer is 1,356. And those are pounds. Okay, now do you have to keep the units in your work like this all the way through? No, of course not. Most of us don't. However, it's really important that you start up here with some organization so that you know you have inches in the denominator, square inches in the denominator both times. And that, of course, means that you're going to do the same thing in the numerator. If I have pounds up here, we should expect some pounds over here. So the organization will help us out. All right, let's find some things that have context. And flip the page. The first time we're going to see proportions will be when we talk about direct variation. Direct variation is reserved for quantities that are directly related. And I know that's really not very helpful, but let's highlight this, directly related. And the thing about being directly related is that they have a constant quotient. And you remember that quotient means the answer you get when you divide. That's, of course, why the fractions are involved in the first place, right? Fraction means to divide, so you've got a division on the left, gives you the same answer as the division on the right, and they have then that constant quotient. If quantities are directly related, then they either increase together or they decrease together, but not in an adding or subtracting way. They increase together or decrease together according to the same factor. And factor is a word that we use when we're multiplying. So what that means is that if you double 1, we'll say it's x. That means or forces you to double y. And that would mean that x and y are directly related. If you, took half of x, that means that you're only going to get half of y. So these things go up and down together, but in a multiplying or dividing sort of way, not an adding or subtracting sort of way. Let's look at an example. We have a blueprint looking at a house. And on the blueprint, the front edge of the house is 10 inches long. But of course, the house isn't really 10 inches long. The front of this house measures 42 feet. On the same blueprint, the back patio is 4 inches wide. And our job is to figure out what the actual width of the back patio is. And the first question is, are the measurements on the blueprint directly related to the actual measurements on the house? And the answer to that is yes. Okay, well, why? Because if you double a distance on a blueprint, you expect the measurement on the house to be twice as long as well. So when you increase the inches on the blueprint, oops, not of, but on, erase. There we go. On the blueprint, then we are increasing the feet on the house. and the other direction, right? If a dimension on the blueprint was smaller, then the dimension on the house should be smaller in exactly the same sort of multiplying or dividing sort of way. Okay, so the quantities are directly related, and our job then is to set up a proportion. Having a table like this is really helpful. It keeps all of your measurements organized. You know exactly what each fraction talks about, you know exactly what the numerators talk about, you know exactly what the denominators talk about. And having a nice framework like this means that you can then refer to it when you get done, and we don't make mistakes when we start talking about the units that are going to be on our answer. All right, so let's see. We'll start with our proportion framework and see what we can fill in. On the blueprint, the house is 10 inches. So we don't need the units in here because I've already got inches over here on my label. Happens to actually be 42 feet wide. The back patio is 4 inches on the blueprint, and I don't know how many feet wide it is in reality. So now we have a proportion set up. And you already know how to solve things like this. So we're not going to take a long time talking about the process, but we'll just go through it like usual. I have a variable in the denominator, and what that means is that we need to multiply both fractions by both denominators. So I'm going to make mine sort of long. The first fraction on the right was 4 over x. The fraction on the left was 10 over 42. But then I want to multiply both of them by both denominators. So I multiply by an x and by a 42 on the right. I'll multiply by an x and by a 42 on the left. And you already know what's going to happen here. We're going to have a lot of things that cancel out. X cancels with x. 42 cancels with 42. Not a bad idea to clean up what we have. On the right-hand side, we have 4 times 42. On the left-hand side, we have x times 10. I'm going to scroll up a little bit. You know how to get the x all by itself. You're probably way ahead of me. Undo the multiplication by dividing both sides by 10. Save the calculations for last so that we don't have any issues with rounding. Cancel out those common factors. And x is equal to 4 times 42, all divided by 10. And that's why we have calculators. So we have 4 times 42. Not that you couldn't do this by hand, but our calculator's right here, so let's just use it. There we are, 16.8. 16.8. 16.8 what? So now you'll remember we've got this organizational chart up here. This x was down here in the denominator, so it's talking about feet. It's also sitting in the column on the right, so it's talking about the patio width. When you go to interpret your answer, we already know now that the width of the patio is 16.8 feet. So you want to use this chart to keep track of your units. Otherwise, it's not so bad, right? Okay, let's move on to another one and flip the page. Okay, so we already know that if we're talking about direct variation, the two quantities have that constant quotient. The actual value of that quotient has a name, and it's called the coefficient of variation. You've heard the word coefficient before. You've seen a coefficient out in front of a variable, where the variable and the number were being multiplied. This is called a coefficient of variation because if you tried to make a graph of blueprint measurement compared to house measurement, then the graph would involve a number being multiplied by one of those quantities. That's something that we'll learn in some other class, but you should know the right terminology for things. So if we were looking back at the example we just did, and we wanted to talk about the coefficient of variation, we'd be talking about some sort of thing that we use to multiply things by when we're working with blueprints. So on a blueprint, the coefficient of variation is known as the scale. You've probably seen map scales before when you're driving. You've got a little thing down at the bottom with some hash marks, and it tells you, that 1 inch on the map is worth 50 miles on the real road. It's the same thing for a blueprint. Sometimes it's called a scale factor. So if we went back and looked at that house fraction, we had 10 inches on the blueprint compared that equated to 42 feet on the house. And if we divided both of these quantities by 10, that would give us 1 inch on the blueprint for every 4.2 feet on the house. So this is inches, and this is feet. The same thing happens when you look at the porch fraction. We found the porch with 4 inches on the blueprint to be worth 16.8 feet in actuality. If I divide 4 by 4, I get 1. If I divide 16.8 by 4, I will get 4.2 again. Of course, that's the whole point of direct variation, is that with direct variation, these fractions have to match. Sometimes they match they will always match, but sometimes we look at them as fractions, sometimes we look at them as decimals, sometimes we look at them as unit rates or unit ratios. It's all the same. Both fractions have to be equal. So what we really know now is that for this particular blueprint, 1 inch on the blueprint represents 4.2 feet on the house. Let's try another example and slide down to the bottom of the page. All right, we've talked about ratios before, and we've talked about compression ratios in particular. Here we have a compression ratio of 5.7. Suction pressure is 31.4 psig. We want to know the discharge pressure. So you'll remember that the compression ratio is the ratio of the discharge pressure to the suction pressure. So ratios and rates are really handy for scaling things up and scaling things down. This compression ratio of 5.7 means we have 5.7 psia in discharge pressure for every 1 psia of suction pressure. So we can instantly make that fraction. Let's see, suction pressure is 31.4 psig. Now don't write 31.4 down here. That's not where it goes. It is sort of where it goes, but we have to be careful of these units. Remember that with compression ratios, we need psia. So 31.4, whoops, don't want that to look like a 9. 31.4. How do you get from psig to psia? You have to include atmospheric pressure. 31.4 plus 14.7 is 46.1 psia. All right, this one was psig. All right, anyway, back to the proportion. 46.1 PSIA in the denominator, x up here in the numerator. And now we're ready to work. Here we go. 5.7 over 1 is equal to x over 46.1. I made my fraction bars extra large so that I can multiply by 46.1 on both sides of my equation. Watch the canceling that happens. This one's actually super easy because there is no extra calculation after this at all. X is whatever 46.1 multiplied by 5.7, whoops, 5.7 is. All right, 46.1 multiplied by 5.7 comes out to be 262.77. 262.77 what? Well, here we are. That's actual discharge PSIA. We should probably turn that back into PSIG since that's the way they gave us the information. So 262.77 PSIA minus atmospheric pressure 14.7 gives us, oh gosh, I don't know, 262. I should probably be able to do this without a calculator, but I haven't had a sip of coffee in a little while, so better safe than sorry, I guess. There we go, 248.07. Now PSIG. So the discharge pressure is 248.07, or we could probably have just rounded to 248 PSIG. And there we go. So you see how nice it is that we've got this table here to keep ourselves organized. Even if you're not going to use the units in your calculations on the way through, start with them to begin with so that you know what your variable stands for and you make sure that you've got the right numbers in the right places. Doing good math on bad setup just gives you garbage. You can always program a computer or have somebody else type things into a calculator for you, but you've got to tell them where things belong. And if you've got things in the wrong places, you're just going to get junk. All right, let's flip the page. Just a little bit more here. Two more things to talk about. When we were in the lesson about ratios and rates, we talked about pitch. Pitch sometimes comes as a ratio, pitch sometimes comes as a rate, depending on what we're talking about. But pitch always describes quantities that are directly proportional. And so this is kind of nice as a picture, because now we can see that if you've got a ½ inch of rise for every 4 feet of run, that when you double the run, so we make it 8 feet long, then we've also doubled the rise. And of course, if you triple the run, make it 12 feet long, then you get 3 times as much rise, or 1½ inches. So doubling the run doubles the rise. And tripling the run triples the rise. And that's how we know that these things are directly proportional. Doubling is a good test. You don't have to use lots of different numbers, but just asking yourself, if I double this quantity, what happens to the other quantity? And if it also doubles, you have things that are directly proportional. So let's try our last example here, because pitch works exactly like a scale factor, and we've already done things with inches and feet. So we'll skip an actual problem that involves pitch, because besides that, there's another one in the reading anyway. So let's check out example 4. Krupa is going to insulate her attic. Her attic is 1,400 square feet. This is going to require 35 rolls of insulation. Phil wants to do the same thing, but of course his attic is a different size, and we want to know how many rolls of insulation he's going to need. This is a fairly simple and straightforward problem. You've probably done many things like this before and not even realized that you were working with direct variation or that you could use a proportion. The whole point of this particular problem is, well, to point that out. Are the rolls of insulation and attic area directly related? Absolutely. This is a yes. But of course, the real question is why? Because if you double the size of the attic, the attic area, what does that mean? Well, it means you're going to need to double the number of rolls of insulation. And really, that's the test. That's how you can tell if things are directly related. All right, so let's set up a proportion and use some labels. Remember that the numerator of the fraction has to describe something, the denominator of the fraction has to describe something, and each fraction itself has to have some organization as well. So let's set up something that talks about attic area, some square feet, and we'll compare that to the number of rolls of insulation. So our fractions are going to look like that. We're going to need one fraction for Krupa's house and another fraction that describes Phil's house. Okay, so from here, since solving proportions is not all that difficult, you should pause the recording and fill in the proportion and work it all the way out to the end, and then come back when you're done. Okay, so you're back. Let's see how your work compares with mine. Hang on just a second. Does your proportion look like that? It should. And then we need to solve it. We notice that the denominator contains the variable. So we want to multiply both sides of the equation by both denominators. So we have 1,400. Oops, that didn't come out very nicely. That was already there, but that needs to be multiplied by 35 and by x. On the other side, we have 2,350. Multiply that by 35 and by x. And don't forget that we still had an x in the denominator on the right-hand side and the 35 in the denominator on the left. Right, x's cancel, 35's cancel, and we see what we have. 1,400 times x is equal to 2,350 multiplied by 35. And of course from here, you know it's nice and smooth. Isolate the variable by dividing by that coefficient. There's that word again, coefficient, right? Of course, these 1,400s are going to cancel. X is now all by itself, and we can do the division. 2,350 multiplied by 35, all divided by 1,400. Whoops, that's not right. Good thing we have a sense of what this answer should be, because Krupa needed 35 rolls and Phil's attic is larger. I see that I missed the 5 when I was typing. Let's try this again. 2,350 multiplied by 35 divided by 1,400 is, that looks a little better. X needs to be 58.75. 58.75, here we are down in the denominator, rolls of insulation for Phil's house. Phil needs, let's say, with 59, you can't buy part of a roll of insulation. Well, maybe you can, I don't know, but certainly not at the store. It's pretty close to 59 anyway. So Phil needs 59 rolls of insulation. And the last thing that we want to look at is this coefficient of variation. What is the coefficient of variation? Just like we saw before, it doesn't matter which fraction we use. We can use the one here for Krupa's house, we can use the one here for Phil's house. If we take Krupa's house, we have 1400 divided by 35, but that 1400 talked about square feet, and the 35 talked about rolls of insulation. So when you come over here to your calculator and take 1400 and divide by 35, that's 40. This means 40 square feet per roll. And this, of course, is the type of unit rate that you would have gotten as an answer during your last lesson. So coefficients of variation here for direct variation are usually unit rates or unit ratios. All right, and that's about it. So the homework for this shouldn't be too challenging. Give it a good shot. Don't forget to keep your organization intact, and we'll talk to you later. Have a great day. Take care. Bye-bye.